I'm sorry, this is the only time I'm going to argue, but you got a whole football season where you could have student section. They don't have homecoming. You got a regular homecoming. You were on the court, but you got it. You were on the court. I didn't say that because that's rude. You should have said it. I should have, but I'm not going to because if my mother saw it, she'd get mad. Okay, I don't know how to do any of this crap. I'm so dead.
Yeah. What did Tucker was just saying how she got?
Well, Tucker was just saying, like, grow up. Like, you're in college. Like, it doesn't matter. It's in the past. Like, stop getting mad because we get stuff, but we get a homecoming and a...
It's not even normal. Dude, are you
Well, I said that too.
about the JV game?
Yes, because this girl was going at Tucker saying, actually, you get homecoming, you get football games, you get this. Actually, we didn't get to go to baseball games. At football games, there's only a certain number of people that can come and get no student section. We can't go out on the field. And then homecoming is at a JV game, not at halftime, and not with all the people that we want there. So actually, it's not the same. Not arguing, but don't say it's the same.
You're so bad.
I don't have to do this.
That's because you probably didn't watch any of the video.
No, I didn't.
He doesn't make you copy when you have work.
I tell my work.
I mean, I have work too, but I still log on if you let it run while I'm working.
I can't. Chick-fil-A, they don't let us in at hot on cold meetings.
I just thought you said before you was I've given you plenty of time to ask them work or whatever you like.
Like, I'm
Okay,
going
that's
to
just
Chick-fil-A
the
one day a
way
week.
it's like-
Exactly. That made me so, I text my mom and I was like, because she told me not to argue on Facebook. And I was like, okay, I commented on this one thing. So you see it, that's what I did. But yeah. So then she went and read the post and she said, you could, calculate the number of days that they missed school last year and compare it to the days you've missed because you're only running 2 days a year. And I was like, they only missed like 50 days.
I don't know, but we're going that.
For a month and a half.
I'm really not gonna be able to work out. Well, actually, I can go into work at 12, so I'm anxious to start.
Well, good morning.
Good morning.
To the four of you that are here.
Oh, thank you.
You're what?
Thank you for the scholarship.
Oh, are you going to eat before?
Huh? No, because there's a Is it paper?
I know, I saw that, but I can't believe it beat anything.
I mean, I'm going, well, me and Hannah talked about last night was just even one. Because it's already an hour away and we're doing pictures at 3.
Why?
And that's the only time she puts it on. So I'll have to be ready like before then. So I have to make my hair appointment early that morning. I don't know who's gonna wait. I don't know. Because my only got ready to do it too.
For homecoming board? I think, so voting is at
Today.
3:30 today. So I
I'm
can,
on.
we'll find out tomorrow, yeah. And then the student body will vote next week. Is my understanding. But I need them to like go and announce the board, because
It said you can only vote for 5 people, but you can like click as many as you want, so I voted probably 10.
I think it was, you could vote for how many people you want, it was the
You got homework to show
rankings
me? I assume.
the rankings were based off of, like, if you voted someone in the number 1 spot, they got more points than if you voted someone in the number 2.
I know, but I thought it literally said choose 5 people and rank them.
Oh, I'll have to put like,
So I felt like 10. Well, not, yeah, I apologize.
I put between 7 and 10.
But I just put a
I
couple
had it
people,
now.
I put like 2 people for 2, 2 people for 3.
I put 2 for 1, 2 for 2, 3 for 3, 2 for 4.
I just put myself for 1.
Huh?
I just put myself for 1. Oh my gosh,
What? If you want to. I need some chocolate, my head hurts right now. Thank you. Thank you.
Okay. I want to start talking about a couple of things here. Start by talking about a couple of things here. Number one thing I want to talk about, we're grading unit 4 test. It was abysmal. It was absolutely abysmal. Aside from the 4 people that got a decent grade, class average is in the D range. Class average in the D range. You know what I find completely unacceptable about it? The number of you all that turned in questions undone. That's not acceptable for an AP calculus course. The time frame that we're turning in our test is entirely too late. It tells me that we're waiting too long to do our test. This is not the first time that I've noticed this, but it is the first time that it has become this big of an issue. Out of the 17 tests that turned in, because I still have somebody who hasn't turned in their test, even though it was due a week ago. The 17 of them that are turned in, 15 of them were all turned in between 11:30 and 3 in the morning. 3 in the morning. So there's a number of issues right there. We're waiting too long to do our stuff, or we're waiting too long to submit it. Either one. Number two, I sat down and talked with some parents last week. They asked, what can I do to help them score better? Not that you guys did terrible in the first 6 weeks or first 9 weeks. In fact, it was actually better than what I expected. But we're not off to a good start this time. Not off to a good start this time. And I told them all the same thing. We need to take advantage of the opportunities in front of us. We had so many questions, we had so many things we didn't understand that we had to leave any questions blank or had no idea how to do them, that we were that far off from the correct manners of doing things. Why does nobody show up for tutoring? Why did we don't ask questions when we start class every day? For this test, 3 people showed up to tutoring to ask questions, and they were the only people that got those questions right, actually. Well, I shouldn't say the only people, but at least they got those questions right. I sat there for the other 40 minutes of tutoring with no one else showing up. Yesterday, you had your quiz come open. Unit 5 quiz came open yesterday morning. Not a single person came by. So that must mean that we're all going to get 100% on this quiz. We're not going to need extra time, and we're going to have it all in by tomorrow evening, right? I understand some of you are frustrated. I get that. Class is hard. I forewarned you class would be hard, though. And I don't know if other things are getting in the way, other classes are stacking up. I've tried to be understanding, but I am running out of patience with some of you. I have a limit to my understanding, which is the point where we're not taking advantage of the things I'm providing to you to ask questions. Every day I start class by asking for homework questions, asking how the quiz and test are going. If we don't know what's going on and we're not showing up and asking questions in class, how am I supposed to help you? We're not coming to office hours, how am I supposed to help you? I want to. I care about your grades just as much as most of you do. Maybe not as much as some of you, because some of you guys are a little bit crazy about your grades. But I can't help you if you don't let me, and you don't ask questions, and you're not involved. And it's not just you all sitting in here, it's the 2 that are absent today, and it's the 12 that are supposed to be on live stream, and there won't be 12 because it never is. The simple fact of the matter remains is there is a handful of us, and more than a handful of us, I should say, honestly, that aren't doing everything we need to be doing in general to be successful. Whether it's work's getting in the way, whether it's other classes are getting in the way, we're not doing everything we need to do to be successful. And this is part of being in this class and part of what I'm trying to prepare you for college, is you think college life is always going to be easy. College life gets hectic, gets chaotic. Things get busy. You have to find a way to get balanced still and get the grades that you need to get. And if that means other things got to go by the wayside, then it does. I'm not telling you to quit your day jobs, but I am telling you that we're going back to school 4 days a week. That was the school board's decision. That doesn't change my class. It doesn't change how anything works. I'm going to tell you, it puts you guys generally at a little bit of a disadvantage. Because some of you told me, I spend 4 or 5 hours on your test. I don't know what you're spending 4 or 5 hours on. I understand I write the test and I'm the math teacher. But I do the test new every time I rewrite them every year. And it only takes me 40 to 45 minutes to do it. Tops. It should only take you guys about 3 times that. So about 120, maybe 160-minute total. When we come back 4 days a week, whatever quiz or test I'm giving you, you have a class period to do your quiz. You might have 1.5 to 2 to do a test, and that's going to be it. I'll let you continue to use open notes and on those things for quizzes and tests, because that's what we've done so far. I don't see any point in changing that for the last 4 weeks of class. But we gotta figure some things out here, gang. Unit 4 was abysmal. And I don't know why, because we did just fine on our quiz, but most of us couldn't turn around to do almost the exact same question on our test. Number 16 on our test is our single most missed question, and it is almost the exact same question as it was on your quiz. The only difference is the shape of the graph. Other than that, that's it. It is done almost the exact same way. So I don't know how we do something once and not know how to do it twice. And that comes, I think, from panic, waiting too long to do it, not bringing questions to class. We got to be better. To say I'm a little disappointed is an understatement. There was only one question on that whole test that we didn't see once before, and that was number 17. And 17 was not that exceedingly difficult, considering that you have open notes, you have your book, you have all the resources. You could have emailed me and asked me how to do it. I don't have much sympathy for us on this particular topic. We need to do better. If we don't do better in Unit 5, that means I'm probably going to have to scrap Unit 7 and go back and reteach 4 and 5. Which means even less that we're prepared for our AP exam. And it does really come down to just doing the things that you guys know you got to do to be successful. Showing up to tutoring when you're not doing well, coming to class with questions prepared, actually coming to your live stream sessions. It's those types of things we got to execute on. So, all that being stated, do we have any questions on 5.3? Where we left off is what we did Tuesday. I'm going to finish this problem I put up on the board because I know that we had some issues at the end of class with this particular example, so I came up with a new one to put up here for us. Do we have any questions on 5.3? Any questions in general? Maybe quiz related?
Number 8 on
On
5.2, number 8.
number 8. Go grab my sheet here. Well, let's go ahead. Let's take a look at number 8, 5.3. We want to find the equation of the tangent line to the inverse of this particular function right here. So, we want to find the equation of the tangent line. So what is that asking us for? The derivative, right? Do the derivative, plug in a point, right? Okay? And we want this for the inverse. Yes? Okay, so looking at this one in front of us, that ain't going to be a fun thing to take an inverse of, is it? Okay, so what should we do first? Derivative? Okay. Take the derivative of, well, not this function. Right here. We got x cubed plus 8x plus cosine 3x. We take the derivative, I'm going to get 3x squared plus 8x. Derivative cosine is negative sine 3x times the derivative of what's inside. So I'm looking at negative 3 sine x. It's my derivative here. First derivative of f.
It's just plus 8, though. Not 8.
Yeah, I should just have plus 8 there. Okay. I do need this. What else do I need? This goes hand in hand with our warm-up problem here today. So that's probably why we might need some help with this one. Plug in the values. What values? I don't need to plug in 0. Just 1. Just 1. And what's more is I don't actually want to plug that in right now. Let's talk about my warm-up problem, and then we'll come back to this one, okay? Let's talk about my warm-up problem, because this is just an extension of this one here. So for you to finish out this problem, what you need here, y minus y1 x, or m, x minus x1. Now here's the thing, is with this being 1, 0, you actually already have this. But what you want to remember here is this is going to be for f inverse, f to the negative 1. So that means these two are going to flip their roles. So 0 becomes an x value and 1 becomes a y value. So what you need here is m. What you need here is m, which is where this will come into play, but it's going to build off of what I'm going to show you over here. For you to find m, you have to be able to do what I'm going to do over here just for that problem. And this is where we got in trouble before. So here's my function. I want the inverse. I want the derivative of the inverse at 5, at the specific point of 5. Okay? So if this is a point of 5 for the inverse, if that's going to be an x value for my inverse, that means that it's a y value for my original function, right? So what I have right here is telling me that this is going to be the y value of this point here. 5 something right there, right? That's what happens with an inverse is we switch x and y. So before I go any farther, I want to find what is its original x value. Okay? So the best way, of course, to do that is to go to decimals. Now, I'm not going to do that right now because obviously I can't pull that up on the live stream. And you can take my word for it. The y value here, or the x value here, is 2, 5. So when I graph this original function, I see I have the point 2, 5. This is the point we're going to focus on when we look at this. Okay? Now, when we talk about the inverse, x and y flip their role. X and y flip their roles. So if it was an x value, it's now a y value. If it was a y value, it is now an x. Okay? We're going to set up the formula that we talked about towards the end of class. The formula here for the inverse function derivative at a specific x value. So what does that look like for us? Well, it's 1 over the original function's derivative times, or with the composite of the inverse. So what this means is we're going to take the inverse function, we're going to get the value out of the inverse function, and then put it into the original function's derivative. This is what we need to do to find m over here. Okay? Are we all okay with this understanding? Now, this should actually be easier than what you anticipate. First and foremost, you already know this right here, because this is this point. As I told you before, x and y flip the role. So if this is an x value for inverse, that means it's originally a y value for the function. So that's why I bothered finding what 2, 5 and writing that out. This is our original x and y, but when we're talking our f inverse, it switches to y x. Does that make sense? So I know that this is going to become 1 over the derivative. This here, when I plug in 5 to the inverse, I should get back 2. So that's what I'm going to plug into my derivative of the original f value. So let's find the derivative of the original f value of the original function. That's going to be 3 over 2 x squared plus 1. Yes? Okay, so I'm going to take this 2 and plug it in. So I'm going to have 1 over 3 halves, 2 squared, plus 1. That's going to give us 12 over 2, which is 6. 6 plus 1 is 7. 1/7 here. Okay? Good so far. So going back to this problem over here, number 8, What I need is I need m. For me to find m, I'm going to repeat this process over here. So when I set this up, this is going to be the inverse function derivative at what point? At point 0. 1 over derivative inverse function of 0. This is going to become 1 over the derivative function. What am I going to plug into the derivative function? It's going to be 1.
So the points that were given were for the original equation, not the inverse?
Mm-hmm. It actually is for both. I mean, if it's a point of the inverse, it's a point of the original equation as well.
Right.
Does that make sense?
Yeah, but I'm saying like when you plug 1 into the original equation, you don't get 0. But if you plug it into the inverse, you do get 0. So I thought it was the point of the inverse already. Like I didn't think you would have to switch it.
Say what you said again.
So what you're saying is that that point comes from the original equation, but
Yes.
it doesn't work out that way. Like if you plug 1 into x cubed plus 8x plus cosine 3x, you don't get 0. But if you plug 0 in, you get 1. Like it's already inverted.
Mm-hmm. So what they did there is I think that they were just trying to maybe do too much to help you guys out with this question. So I do understand what you're saying there. And I misread the question. So I think you're right there. These need to swap. So the original point, so 1, 0 is the -1, -0 here, making the original point in black 0, 1. Which does change this just a little bit. So that means when I plug in 0. So 0 needs to go into the derivative. Thank you, Bianca, for helping us set that straight. 0 going into the derivative, that's going to be 1 over 3, 0 squared, plus 8, minus 3 times sine of 0. Just a little simplification there. Sine of 0 is 0, so that goes away. That goes away, and I got 1/8. So I'm looking at y equal to 1/8 x minus 1. Further questions here? So, what this whole little formula does, and why I've taken like 20 minutes of class to do it, is 1, because we didn't understand it the first time around, and 2, this allows us to find the inverse derivative at specific points, especially when finding the inverse function is not something that is easily obtained. I can't just do what we did for most of class on Tuesday. I can't just look at either one of these original equations and say, okay, I'm going to swap x for y and then isolate. That's not going to be an easy feat by any stretch of imagination to accomplish. If it was, then that's what we would do, is create the inverse function, then do the derivative, and everything would be fine, and everything would work easily. This is what to do when it can't be that easy. If I swap x and y here, you're not going to isolate that easily. If I swap x and y here, you're most definitely not going to find that easily. So this is how we do it when it's not so crystal clear. When you can't just generate the inverse function and then do derivatives or integrals on that. Okay, let's talk about what we need to do today, because today's slides are relatively long. Hopefully, it's an easy day. Hopefully. I said that about Tuesday, and it turned out to be a little bit of a lie, apparently. I like to think it was an easy day for at least the first 70 minutes. Let's go ahead, let's jump into what we need to do here today. We're going to talk about exponential functions here today. exponential function. So something to the power of x. We're going to be talking a lot about e today and natural logs and how they go together. We're also going to talk about this again tomorrow too. That's why tomorrow's lesson is basis other than e. So exponential function. So let's start here with e and natural log. It's the basics here. E and natural log, they undo one another. They are inverse operators. They're inverse operators, so the natural log of e to the x is simply x, or the natural log of e is 1, however you want to view that. The natural log of e is 1. So this is some basics here on slide 2 for us. We should know this. We should be comfortable with this, and if you're not, make sure you jot it down. I'll move on to slide 3. So using natural log of e to help us solve some equations. So let's just bring back some pre-calculus, unit 2, unit 3 kind of stuff here. When I look at the first one here, I have 7 equal to e to the x plus 1. So if I wanted to solve this for x, what I would do here is I would start by taking the natural log of both sides. And what's going to happen here is the natural log of 7, and this 2 will cancel, bringing down my exponent as x plus 1. What's really happening there is a power rule, allowing us to bring the x plus 1 out of the exponent and make it a multiplier of natural log e, and then just simply reducing natural log e down to 1. And then if I really want to be thorough, natural log minus 1 equal to x. That's how we would solve our first one here on slide 3. Likewise, the one next to it, natural log 2x minus equal to 5. Okay, so I'm going to just go ahead. I'm going to raise both sides to make them exponents of e. Make them exponents of e. There's a property here that if I have bases that are the same, then the exponents must be the same. I can use that reverse, that if I set exponents the same to the same base. This allows me to cancel these two and make this 2x minus 3 equal to e to the 5th power. E to the 5th power is a number. It's a decimal. It's not something that we're going to work too much with. I don't always recommend reducing them down. If you want to finish this out, of course you can. It's just simple algebra from here. E to the 5th minus 3 all over 2 is what we're going to be looking at for our final answer, or whatever decimal that's going to spit out. Questions here? Vaguely familiar. You're going to want these skill sets today. You're going to want to remember these as we work more and more into natural logs and e. So, some basic properties otherwise about e, of course, is e operates just like any other number. E itself is just like, it's similar to pi. It's a constant that we use for specific settings. It's just the constant for natural logs, whereas pi is a constant value for circles. When we see it, we should just think about it as just being a regular old number, a 2 or 4 or something like that. So if I have it being multiplied with another e, I can, of course, add those exponents. I can subtract exponents if they're stacked in fractions. All the exponent rules still hold true here for base e. That's what you see on our next slide here. What is it? Slide 5 now. I think I'm on 4 or 5 now. 4. Okay. And some brief examples here for each of them. So let's talk about some fun stuff with e. So here's the fun thing about e is e makes derivatives and integrals, I guess, easy or complicated, depending on the way you want to view it. The derivative of e to the x is just simply e to the x. The derivative of it is the exact same as the original function. And if I had time, I'd show you, but I really don't. Just take my word for it, or look at your book. This doesn't change a whole lot when we talk about doing a chain rule for the derivative. So like e to the u would just be, well, the derivative of eu, which is the same thing, times the derivative of whatever is up in the exponent. This makes derivatives and integrals of these relatively easy to do. This makes derivatives and integrals of these relatively easy to do. What becomes challenging about them is the algebra that lets us use these basic properties. So the derivative of e to the x is e to the x. This doesn't change very much when we use a u substitution, except for, of course, we'll do the derivative of the x here, which for us will be e to u, which is just going to be the original eu again. And then we'll multiply by the derivative of what else is up there. Questions thus far? I think this works easiest if I just show you a few problems as examples. Are you guys ready for me to do that? I see a number of you still writing things. Cool. Let's move on to our next slide then. Be on slide 6 by now. So our very first one. So we're going to simplify. We're going to take the derivative. Find the derivative of e to the 2x minus 1. Okay, well, let's make this a very easy chain rule. Let's use some substitution here. U here would be 2x minus 1, correct? What would the du or u's derivative be here? 2. Okay, so when we take the derivative of this, we're going to swap it for eu, which the derivative of eu is eu times u derivative. Okay, so let's bring back x. Let's bring back x. This will be e to the 2x minus 1 times 2, or 2e to the 2x minus 1. Questions here? For easy, simple ones like this one, I'm totally okay if you don't write out the u substitution. For a simple chain rule like this one, I'm totally okay if you don't write out the full u substitution part. Questions? Okay. That wraps up our first example on slide 6. Let's move on to slide 7 then. Move on to slide 7. Let's take a look at one that's a little bit more challenging. E to the negative 3 over x. E to the negative 3 over x. Okay, let's not approach it any differently though. Let's try to use our u substitution. U here will be negative 3 to the x. So I take the derivative of this. What are we going to be looking at here? What's the derivative of negative 3 over x? No. Not quite. This has become x to the negative 1, right? So instead of it being, we take the derivative here, the negative 1 comes down, gives me 3, and I have x to the negative 2nd, or not negative 3, but positive 3 over x squared. Is that what you said? I thought you said negative 3, my fault. Okay. It is positive 3 over x squared here. Questions? All right, let's use our u substitution here. It's be eu, so that means that the derivative here would be eu times u's derivative. When we go back to x, this is looking like it's going to be e to the negative 3 over x times 3 over x squared. All we need to do from here is simplify it down into one nice cohesive fraction or set. So I'm looking at 3e to the negative 3 over x all over x squared. If I want, I can actually take this one step further. Because this is a negative exponent. Technically, it goes on the bottom. So this is actually e to the 3 over x times x squared. This would be its most simplified form right here. Questions or concerns for this one? Okay, let's move on to slide 8. Let's start mixing in some other things that we've talked about, going back to unit 3. I want to find the relative extrema of f of x if that's x times e to the x. How should we do this? When I say find the extrema, what does that sound like to you? What does that heart memories back to? Yeah, we're going to do the first derivative test. That is the best way to still find extremes. That is the best way to find extremes. I don't recommend trying to graph it. I recommend doing the first derivative test. So we need a derivative here. What is this derivative going to look like? How do I find the derivative here? I don't need to do any u substitution or anything. It's actually easier than that. Not quite, because I do have an x multiplier in front of it. We're going to need a product rule here. We need a quick product rule here. So f and g. Fatima, we will use that as part of this right here. Why do I keep doing that? 1 is called the f function, and g derivative here would be e to the x still, right? Okay, so let's set up our product rule here. That's g f derivative plus f g derivative. Okay, well, g is e to the x times 1, so I have e to the x for my first set here. Everybody good there? And then my second one, I'm going to have x e to the x. Questions here? This is a fun function because it just continues to expand the more derivatives you do of it. If I did a second derivative, I would just end up with 2 e to the x plus x e to the x. If I did the next derivative, it would just be 3 e to the x, and you get the idea. It just continues to stack. It's an interesting function, to say the least. Okay, I have my derivative. What am I going to do with it? I would run the first derivative test. What do we look for? Where we have x equal to 0 and where it would be undefined, right? Okay, so let's start with, is there any value that's undefined here? Divide by 0, negative in a root, anything like that? No, because e is just a constant number, right? So we're going to be looking at it's going to exist everywhere kind of function. It's going to exist everywhere kind of function. So we can try to set it equal to 0. E to the x plus e to the x. What are we going to do to solve this out? Factor out the e to the x part of the function. I have 0 equal to e to the x, and I got 1 plus x. So what are we looking at here? Where's our critical value? We should have critical value at x equal -1. Set up my number line. -1. Is everybody okay so far? Are we moving too quickly? Okay. Where do I got to plug in? Where am I going to plug it into? Somebody other than Bianca. -2. And where am I going to plug -2 in? For which one? The original or the derivative? The derivative, okay? So -2 going in here. What are we going to end up with? Gang, I'd make it easy for you. I'd plug it in right here. I would maybe rewrite this as e to the x 1 plus x, just like this, like we have it right here, but just for your plug-in value to make this a little easier. If I put -2 in, what am I going to get here? a negative, right? If I plug negative 2 in here, this is going to be a positive. What's negative and positive make? Negative. Okay, what are we going to put in on the other side? Let's make it easy. How about 0? Okay, 0 plus 1 is 1. Anything to the 0 power is 1. 1 times 1 is positive. So we do have a value here. What type of value do we have? What type of value do we have at negative 1? A minimum? Absolutely. Min at negative 1. Relative min. Questions here, concerns here about this one? If we look through my work here, first thing we did, of course, find that derivative. We set it equal to 0. We found the same critical value to be x equal to negative 1. We set up our number line. I got negative and positive, just like we did here. In fact, I picked the same values, negative 2 and 0. Plug them in. So we have a relative minimum at x equal negative 1 because of the change from negative to positive. Questions here, concerns here. If we kept going with the second derivative test, we could state whether or not this might be an absolute maximum or minimum. We need to know some concavity for that, though. We need to know concavity for that. If this is continually concave down, it's concave down on the entire interval, then this would be, well, this wouldn't be if it would have to be concave up. If it's concave up on the entire interval, then this would be an absolute min. It's not, though. Okay, so let's talk about some even more fun, crazy stuff with e. Of course, if the derivative of e to the x is just e to the x, then that works the other way around too. The integral of e to the x would just be e to the x plus c. This is even easier when you talk about u substitution. If you have eu, then the integral of eu is just eu. There's no u prime, there's no integral of the interior. It's pretty straightforward. It is pretty straightforward. Similar to how we've done this before, if we do rely on our u substitution for chain rule, most of what we're going to do is actually going to happen pre-integral so that we can swap out dx for du. That's really where most of that's going to take place. The actual integral itself should be relatively straightforward and easy to apply. As we've seen with previous chain rules, as we talked about not only in this unit, but back in Unit 4, which I'm questioning how much we understood Unit 4 at this time. That's what we're going to be doing. We're going to be focusing more on beginning before we do the integral, more so than the actual rule here itself, because the rule is just keep it the same and add c. Questions here, issues here. Okay, let's move on to our next slide then. Where are we at here? We should be at slide 10 now. Let's give an integral for this one. I've got a little bit started here for us. We have the integral of e to the 3x plus 1 equal to dx. So since it's not simply just e to the x, we're going to make it into eu, so that way we can do the nice quick integral. That's what we need, is we need an e to the single variable, and we need the derivative dx du to match that variable. So that's what we're looking at here, is I want to swap these to be the same and be a singular item. So that's why we're going to go with u substitution there. U is going to be 3x plus 1. That makes the derivative of u, du, 3 dx. So for me to convert this over successfully for our u substitution, I need to bring in a 3 multiplier inside and a 1/3 outside. This allows me to rewrite this as 1/3 e u d. Are we all okay with my work there? This 3 multiplier that I brought in, this dx comes together to make du for us. And then I've already set u equal to 3x plus 1. Is everybody okay with everything where it came from, where it needs to go? Okay, now we'll just apply the rule that we just talked about. The rule is, of course, the integral of EU is just EU plus C. And all this, of course, times our 1/3 multiplier out front. I guess the plus C should kind of come after that, but it doesn't really make a difference. The only thing left to do here is, of course, to swap back to X. So this will be 1/3 e to the 3x plus 1 plus C. Plus whatever constant we're left with. Is there any questions here? Slide 10. Any concerns here? Slide 10. Okay, let's move on then. Next slide. Let's move on into our next slide, slide number 11. I'm tired of doing these. I'd like you guys to try this one on your own for slide 11. If you get stuck, of course, you can click a little bit ahead and see my steps. Or, better yet, you can ask me a question. Okay, go ahead, let's step through this one. I make u equal to my negative x squared. That makes du negative 2x dx. I already have an x out here, but I don't want this 5, so I'm going to move the 5 out front. I'm going to bring in a negative 2, which means I need to bring in a negative 1/2 to counteract it. So I have a couple of multipliers out in front of my integral now. X e to the negative x squared dx. Now I can go ahead and use my u substitution here. Negative 5 over 2 is my multiplier out front. This becomes eu du. These two coming to make my du. When we integrate, that's negative 5 over 2 eu plus c. So just bring him back to the original, negative 5 over 2 e to the negative x squared plus c. I'll take it just like that, or if you really want to be super thorough, you can, of course, send that down and make it positive x squared plus c like so. Either one of these would work for me. At that point, it's not really about your exponent negative laws. It's more about, did you do your problem correctly? I don't think I would take off points for not going completely the way through. Questions here for this one? Concerns here for this one? Okay, well then let's move on. Let's move on. Number 12. Okay. This one should be pretty easy. This one should be pretty easy. Over x and over x squared dx. When we set up our u substitution here, u would be 1 over x, which of course makes du negative 1 over x squared. Correct? Of course, dx, right? Okay, so the only thing I really need to bring in here is a negative multiplier. So a negative out in front and inside. That allows me to swap this cleanly for EU du. A negative out front, which is just a negative EU plus c, or negative e to the 1 over x plus c. Questions here for this one? Concerns here for, what is it, slide 11, 12, 12. Okay, let's take a step up. Let's try some trig functions. Let's make some trig functions in. What do we need to do for this? I don't have the interest in working it out on the board. Tell me what I need to do.
Set u equal to cosine x.
If u is going to be cosine x, that makes du what?
Negative sine.
So I need to bring in another negative here then, right? So we should be looking at our final answer here is negative e to the cosine x plus c. Everything Bianca's described is on point. As I tried to promise you earlier, today hopefully is an easy day. E to the x is not a difficult function to work. It's not a hard function to deal with. It works really well, really easily. Questions here, slide 13. Okay, let's start doing some definitive integrals then. Let's start doing some actual closed integrals here. Now let's not get too carried away. I'll work the first one just to make sure we're all comfortable. I have 0 to 1 of e to the negative x dx. First thing we're going to do is we are still going to use our u substitution here right quick. U is going to be, of course, negative x. That makes du negative 1 dx. So we are going to need a negative 1 multiplier here out in front and inside. This gives us negative 1, 0 to 1 of x equals 0 and x equals 1 because I didn't switch those over. Of eu du, which becomes negative eu to 0 to 1 power x equals 0, x equals 1. Are we okay so far? Comfortable? Okay. Let's evaluate then. Let's go back to x and let's evaluate. So this is going to become negative e to the negative 1 minus negative e minus 0, just like this here. So this is our negative e to the x, negative x, right there. We all see that, okay? All right, well, this is just going to be negative 1 over e, and this is going to be anything to the 0 power is 1, so I have negative 1, I got plus 1 here. I got negative 1 over e plus 1. Questions or concerns about this one? Not very difficult, is it? Okay. Next one's up. Go ahead, try it. Next one's up. Let's go ahead. Let's try it. Slide 14, 15. Slide 15. All right, let's go ahead. Let's tackle this. What are we gonna do? Maddie, what'd you do?
I said u equal to ex.
Set u equal to.
Ex.
So what I would do, Maddie, is not set it equal to ex, but I'm gonna set it equal to 1 plus ex. Okay? So if I set it equal to 1 plus ex, the advantage there, of course, is that du will be ex dx. Okay? That allows me just to go over here and do a quick substitution for u. This becomes 1 over u du, right? Where this and this come together to form du. Questions here so far? Okay, what's the integral of 1 over a variable? What's the integral going to be here for u? Natural log of u, right? This is why I reviewed that at the beginning of class with you, is because this is helpful right here. Let's go back to x now. Let's go back to x. So natural log of u is 1 plus e to the x, so this is natural log 1 plus e to the x of 0 to 1. Right? So now we're looking at natural log 1 plus e to the first minus natural log 1 minus plus e to the 0. Let's do a little simplifying here, Maddie, okay? First, let's just call this natural log 1 plus e. Let's call this 1 minus natural log of 1 plus 2, right? Because e to the 0 is going to be 1. Anything to the 0 power is, of course, 1, right? And 1 and 1 make 2. Are we okay with what we've done so far? Okay. Now, Maddie, you might be tempted to grab the calculator and punch this stuff in. Still an easier way. These are logs, right? Okay. Can't I combine logs through subtraction? We talked about this the other day. Natural logs can be combined through subtraction. I'm using the quotient property here, and I'm left with 1 plus e over 2. Let's see how we turned out. Let's see how we turned out. So, u substitution looks good. Only one thing that we forgot here, but that's not a big deal, is it should be the absolute value of u, natural log absolute value of u. That's not going to make a big difference for us, though. That only matters, of course, if we have something that's going to spit out negative for us when we plug it in. So I swapped it back over, 1 plus e to the x, 0 to 1. I reduced the exact same way, I left it all the same way. The only thing that I would change here, of course, is that you want the absolute value bars all the way up until about here. At this point, you know that you're not going to get a negative inside here. It's got to be positive, so I don't think there's anything to stress about. Questions here for slide 15? Concerns here for slide 15? Okay, there's another one for you. Slide 16. Okay, well, you're sitting here done, so which one of you 5 want to do it? Okay, Abby, help me out. What'd you set u equal to? E to the x. That makes du ex dx. So when I want to rewrite this as a u substitution, what's it going to rewrite as? Okay, well, you just told me u is ex, right? It was sine u. Take this one and that dx and make them into your du. I would not do a product rule here. I most certainly would not do a product rule here. A product rule could be done here, let's be clear, it could be done. But it's definitely not going to be the easiest thing in the world to do. Let's go ahead, let's integrate. What's the integral of cosine? Oh, I don't think it's negative sine. I think it's just sine. Okay, so when we swap back to x, we're looking at sine of e to the x, correct? Yes? Okay, so we're looking at sine of, well, e to the x, e to the 0, minus sine e to the -1, correct? Okay, what's e to the 0 going to be? 1, okay. What's sine of 1? When the x value is 1, what is sine?
0.
Ooh, I don't know about that. Think about your unit circle. Think about your unit circle. If you're not sure, grab a calculator, type it in. Grab my calculator, type it in. Oh my goodness. Sine of 1 is it's a big old decimal, isn't it? Okay, so this isn't a real good value to actually reduce it down. Okay, don't fall under that trap that it's always going to be that way. Okay. Only other thing that we might want to do here: sine of 1 minus sine 1 over e. Correct. Questions here? This is exactly where I'd leave it, Abby. I will not go to any decimals with it. Now, it'd be a little bit different story if this came out to be sine of 0. 0 is a good radian value, right? Or if this was maybe sine of pi or pi over 2, this would be a good radian value. But it's not. Question? Okay, so that's slide 16. Let's take a look. That's it. That's all I got for today. Take a look at our homework. Take a look at our homework. I want to talk about one more thing before we wrap up here today. Somebody asked me about the bonus that's due for your test. Somebody asked me for the bonus that's due for your test. I didn't put it on. And I'll tell you why completely candidly. Some of you got really, really bad scores, like 50s, 30s, 40s. If I put your bonus on, it's a one-time deal. It's a one-time deal. I can put it on here, but if you're going to do corrections to get up to a 75, it doesn't really help you. So what I'm going to do, I think, is I think I'll wait until you're done with your corrections. I think that I'm going to open up the window for that, and I don't normally cut them off, and I won't. if you can't get to them right away, but I would like to have those done within a week. So by next Friday, I'd like to have our corrections done. So that way we can be looking at going into spring break or going into the week before spring break with relatively updated grades. Now there are some of you sitting in here that don't need corrections. So nonetheless, you're going to have to wait for yours. You have time to work on your homework. Let's just get started.
Could we do like corrections or retest it on the quizzes?
We do not redo quizzes.
Okay.